The purpose of this project was to apply our materials and manufacturing theory to a real mechanical artifacts. We focused on linking design, material choice, tolerance, and quality control to real-world automotive safety applications. The purpose The artifact is a single piston floating caliper. It converts hydraulic pressure into the clamping force on a disc rotor. It's compact, reliable, and one of the most common braking systems used in passenger vehicles today. The brake calipers are mass produced worldwide, over 200 million units per year. This design dominates in compact and mid-sized cars because it balances cost, weight, and performance efficiency. When the driver presses the pedal, hydraulic pressure pushes the piston forward, clamping the inner pads. The caliper then slides to press the outer pad, creating friction torque that slows the wheel. When the driver presses the pedal, it operates under extreme conditions, temperatures up to 300 degrees Celsius, and hydraulic pressures around 8 to 10 megapascal. The expected service life is roughly 8 to 10 years, or about 150,000 kilometers. It Key components include an aluminum housing, stainless steel piston, EN8 steel guide pins, EPDM rubber seals, and high tensile bolts. Each part was selected for its strengths, corrosion resistance, and manufacturability. Precision is critical. For example, the piston bore holds a plus minus 0.02 millimeters tolerance with a H7 slash H6 fit. These tight limits ensure smooth sliding, proper sealing, and consistent braking performance. Precision is critical. Surface finish directly affects seal performance and pet wear. The bore surface is polished to a Ra less than or equal to 0.8 micrometers, ensuring minimal leakage and friction. This image shows the microscopic texture typical of a fine machined bore.
Hi, my name is Ahmed, and now I'll be presenting the next slides. So for the next slide, the brake caliper technical drawings. This slide shows the technical drawings created in SolidWorks for a single piston floating brake caliper. This drawing includes front, top sectional views that highlights the main geometric features. Key tolerances, surface finishes are labeled such as maximum roughness of 0.8 microns on the piston board. All dimensions follow the ISO 2768 MK and AS 1100 standards to maintain accuracy and consistency. The expert view helps visualize how component fits together and supports the assembly process. This slide lists the main materials and manufacturing methods used in the black caliper assembly. The housing is made from the aluminium 6061T6, which offers a strong yet lightweight structure and is produced through high pressure die casting followed by the T6 heat treatment. The piston can be either stainless steel 304 for strength and durability or phenolic resin for better heat insulation in lighter vehicles. Other key components such as EN8 steel guide pins and EPDM rubber seals ensure smooth motion and resistance to brake fluid. Each material was chosen to balance performance, manufacturing, and cost efficiency in line with automotive standards such as ASTM B221 and ASTM A276. This, this slide shows the bill of materials for the brake caliper assembly created in SolidWorks. It lists all the major components, including the brake disc, housing, pistons, guiding pins, fasteners, along with their quantities. Each component is labeled and numbered to match the technical drawings. I help identify how parts interact during assembly. These materials use range of aluminium for the housing, steel for the fasteners, and composite pads for friction. The structured bill of materials is essential for manufacturing planning, inventory management, and ensuring that all the components meet their respective material and dimensional specifications. This slide outlines several alternative materials that can be used instead of the aluminium for black calipers. Cast iron remains a traditional option for heavy duty or budget vehicles because it's cheap and easy to cast, but it's heavy and prone to rust. Titanium alloys are incredibly strong and corrosion proof, ideal for racing brakes, though their high cost limits the production use. Magnesium alloys offer excellent weight reduction but require protective coatings due to poor corrosion resistance. Carbon fiber reinforced polymers are lightweight and stiff, used in high performance racing, but are expensive and complex to manufacture. Overall, the aluminum 60616 remains the best option, compromised between the strength, cost, manufacturability for standard automotive calipers. This This table summarizes the performance trade-off between the material used in brake calipers design. The aluminum 60616 is preferred for housing because it's lightweight, corrosion resistant, and provides good heat dissipation, though machining costs are higher. Steel offers strong mechanical performance but adds weight and requires surface protection to prevent dust. Stainless steel provides durability, heat resistance, making it suitable and for pistons and fittings, though it increases the cost. EPDM rubber seals resist brake fluid and weathering, while cast iron remains a low-cost option in older caliper designs. Overall, this material was selected to balance the cost, performance, and compliance with ASTM and ISO standards. This slide outlines the manufacturing process flow for the aluminum brake calipers. The process begins with die casting, which forms the housing for minimal material waste. Next, the T6 heat treatment is applied to increase the hardness and fatigue strength. CNC machining then achieves precise tolerance about 0.02 millimeters, especially for the piston bore and mounting holes. After machining, the anodizing is used to improve corrosion resistance and surface appearance. Finally, the parts go through assembly and hydraulic testing to verify the dimensional accuracy and leak-free performance. This process flow ensures that each caliper meets both mechanical and quality assurance standards required by the automotive industry. This slide highlights the main equipment used in brake caliper manufacturing process, and the die casting machine forms the aluminum housing using a high pressure injection supplied by the manufacturers like Buller or Uzumi, and must comply with ISO 9001 or ISO 1401 standards. Next is CNC milling and turning centers from companies like Haas or DMG Mori perform precision machining on bores, threads, and mounting holes, ensuring tight tolerances. A lathe is used for cylindrical components such as pistons and guide pins. For quality control, peripherometers and coordinate measuring machines (CMMS) from Zeiss or Mitutoyo verify dimensional accuracy and surface finish. Finally, hydraulic testing bench checks for leaks, pressure resistance, ensuring each assembled caliper meets automatic testing standards. This slide compares several alternative manufacturing processes that could be used for producing brake calipers. Sandcasting is a low cost, suitable for large components or low volume production, but has poor dimension accuracy and rough surface finish. CNC machining from billet delivers excellent precision and surface finish, making it ideal for specialized or prototype calipers. However, it's time consuming and results in higher material waste. Powder metrology is a more sustainable process, generating a minimal waste, consistent properties, but it's limited to a smaller parts, has lower fatigue strength, and overall die casting remains the most efficient process for mass production due to its precision, repeatability, and low waste generation. This slide highlights the environmental consideration of manufacturing an aluminum brake caliper. The first aluminum recycling is highly energy efficient. It saves about 95% of the energy compared to the producing new metal from the European Aluminium Association. Waste reduction is achieved by collecting and machining chips and reusing them as a feedstock in die casting. For surface protection, water-based anodizing and powder coatings help reduce the volatile organic compound emissions. In manufacturing, used calipers can landfill waste by up to 70%, while the use of electric CNC machines can lower the CO2 emissions by 20 to 30%. Finally, the aluminum components are fully recyclable, and all the polymer seals can be recovered at the end of the product's life. The diagram below shows the life cycle from raw material recycling, emphasizing the circular nature of sustainable brake caliper production. This slide covers the quality assurance and inspection process that maintains the consistency and reliability in brake caliper manufacturing. Production follows ISO 9001 and General Quality Management and IATF 16949 for governs automatic manufacturing standards. Performance testing, the process complies with SAE J1401, ensuring the hydraulic integrity and safety. The key test includes the dimensional checks using the CMMS following the ISO 1101, ensuring all parts meet the precise geometrical tolerances. The surface traffic testing with the profilometers to verify the required area values under the ISO 4287. Pressure and leak testing at 10 to 12 megapascals to confirm the sealing reliability. Hardness tests per ISO 6508 to ensure the correct material treatment. Finally, the visual inspections under ISO 3059 identifies any surface or coating defects. Together, these produce ensure each caliper meets the structural, functional, and safety standards before leaving the production. This slide outlines the verification and testing methods used to confirm the brake caliper meets design and performance specifications. Each inspection follows the international measurement standards for consistency and traceability. First, dimensional checks are performed using a coordinate measuring machine following the ISO 1101 and ISO 26861 to verify the bore diameter and spacing accuracy. Next, the surface roughness is assessed with a profilometer under the ISO 4287, ensuring that the required area value for sealing and wear control. The pressure leak test applies to 10 to 12 megapascals of hydraulic pressure following the SAE J1401 to verify the seal integrity. Hardness testing under ISO 6508 confirms the proper heat treatment of machine parts. Then the visual inspections check for cracks, coating defects per ISO 3059, while the corrosion resistance test the salt spray chamber comply with ISO 9227. Finally, the functional testing on a dynamic rig ensures that the piston movement and retraction operate reliability, meeting the IATF 16949 compliance standards. These verification steps ensure every manufactured caliper is safe, dimensionally accurate, and ready for use in automotive applications. This slide presents the estimated production cost for one brake caliper unit. Total cost is approximately $51.50 AUD based on the data from local suppliers and manufacturing references. The raw material aluminum 60616 contributes about 12% of the total cost, can be sourced from caproled or urological aluminum. Die casting costs are relatively low at $2.50 provided by founders at Intercast and Forge. The largest portion, around 58, comes from the CNC machining, which includes the milling, drilling, and threading operations performed using the equipment from Haas or DMG Mori. Surface finishing such as anodizing through Surface Technology Australia adds another 10%. Finally, the assembly and the inspections carried by manufacturers like Roma Engineering New South Wales make up to 16% of the total cost. As shown in the pie chart, machine and labor are the major costs driving the drivers. Optimizing die design and using the automation could reduce the cost by up to 15%. To conclude, this project successfully demonstrates how materials, design, and manufacturing theory are applied to a real automotive brake caliper. The purpose was to apply engineering principles to a safety-critical system and analyze its function, materials, and tolerances, and connect theory with practice. The artifact, a single piston floating brake caliper, was selected for simplicity, low cost, and reliability. It operates by converting a hydraulic pressure into clamping force onto a disc, generating the friction needed to slow the wheel. Operating conditions reach up to 100 to 300 degrees Celsius and pressure from 8 megapixels to 10 megapixels. Demanding high material and surface integrity, the main components include AI 6061 T6 housing, stainless steel piston, and EPDM seals were chosen for their balance of strength, machinability, and corrosion resistance. The precision machining to 0.02 mm and surface roughness below the RA 1.6 ensures proper sealing, sliding, and pad connect. verified against the standard like ISO 1101 and IS 1654 and ISO 2768. The production process combines the die casting, heat treatment, CNC machining, anodizing, and testing supported by ISO 901, IATF 16949, and SAE J1401 for quality control. Environmentally, aluminum recycling cuts energy used by around 95%, while machining waste is recyclable. Economically, the total cost per unit is about 51.50 IED, with machining and labor being the largest contributors. Overall, the project met its objectivity by integrating design analysis, sustainable material use, precision manufacturing, and quality assurance, showing how the theory is effectively translated into real-world engineering outcomes. The, the next couple of slides are the references, and that's done. Thank you for listening. Have a good day.